Hello everyone, my name is Konstantin Yakushenko. I am Tools team lead at Frogwares, and today I want to share with you the way how we have ported our modern game from PlayStation 4 in Xbox One to Nintendo Switch. So let's go. The Sinking City Road to Nintendo Switch. Next 30 minutes I will talking about the following: a few words about our company and the games that we produced. Then you will hear about how exactly we decided to start the Sinking City Switch project. Also you find out about the preparation and the research we did to make sure the task is possible to dive into. Later I will explain about what had to be done with the game characters, their meshes, animations, skeletons, textures to fit. Afterward we will move to the part which show our work with the city geometry, world object, city grid, and finally I will show you what had to be done on the code side. Just a little bit about us. Frogwares is an 80-people studio located in Kyiv, Ukraine, that has been around for 20 years, mainly making games featuring the adventures of Sherlock Holmes. Those games are focused on investigation gameplay, which we feel was quite rare and still a bit niche today. After making 11 Sherlock Holmes games, a very logical thing for us was to keep the investigation gameplay in the next project, but with a twist on the setting. Now a little bit about Sinking City game itself. It's an open world investigation game in Lovecraftian setting. I will show you a short gameplay trailer. Almost everything you will see there is an in-game footage.
I'm Charles Reed, private detective. I've come here for some answers. Visions have been getting worse. I believe the source of this madness is here in Nogbot. This city is short on everything except dirt, rain, and things that want to kill you. I want none of this to be real.
Here is, in short, some key input data we had when we started thinking about Nintendo Switch. We have just released Sinking City on PlayStation 4, Xbox One and PC with Unreal 420. This is open world game with a free movement inside the flooded city, and the city occupant is about 2 square kilometers. The total length of the streets is about 33 kilometers. On the time we had full dynamic lighting and day-night cycle and dynamic weather system. We had a lot of different characters, main character skins, NPC crowds, characters monsters. And we had that one Nintendo Switch dev kit laying on the console table near me, and we all knew that we had to try to run our game on it. So we decided at least to try run our game on that hardware. As Unreal started to support Switch since 4.16 and we were at 4.20 at the time, it wasn't that hard. And we just had to install SDK, compile game code, fixing some problem for it, cook the game. In a few days we had the game installed on that dev kit. And it worked. Sometimes it struggled to have more than 10 FPS and often crashed. However, it's worked. It feels fantastic to see this game running on the portable platform. On that stage we did nothing in terms of optimization. A raw PC version running on Switch. But making the game run does not equal to release. After showing the build to the studio management, we were given a green light to conduct the proper research, to find out what exactly it's needed to be done by various studio departments to fit the game into the target hardware. The goal was to find budgets, so we started to profile every aspect of the game: memory consumption, render and game rate, build size. There was not a lot of time to do this migration, so looking ahead, here's our timeline. So 4 months. This is very exact time the migration took us, from the beginning of the production to the final release, including the time for certification process. On this slide you can see the main stages that we passed to achieve our goal. I just wanted to say that I'm very proud of the team which accomplished that task in such short time. So let's see what exactly we did. First, I would like to explain our character pipeline, which used in Frogverse for character creation, before we dive into the optimization process. We combine each character from the separate elements: a head, a pair of arms, legs, etc. You can see the whole set over here on the slide. Our character's artist only creates those components, so-called construction sets. During the production, we created more than 1,170 characters elements for those sets. To get the final characters, the game designer combined different elements in the character editor. You can see the whole process on the slide. And after pressing the save button, we merged skeleton meshes into one pieces and merged textures as well. Here, just an example of textures after merge. We had two different resolutions for different group of characters. For crowd it's about 1024 and for NPC it's 2048. As a result, we got 411 different characters, which we grouped in 3 categories. Main character and his skins, NPC that we can see in max details and dialogues, and the crowd filling the streets, plus monsters that we made in DCC application and then imported in engine separately. But our average character had about 40,000 polygons on consoles, and so dozens of those guys in one frame easily brought Switch render to its knees. And here's some action scenes plus city geometry, and I guarantee you nice slideshow with a 5 FPS and top. So, okay, we need to optimize them and optimize them dramatically. But how do we do it? By making the whole character team to manually redo all those thousands of elements during a month or 2? How much do we want to simplify each character? Is there any way we can automate this process? Is it worth doing all those elements, or better focusing on the final one character? And before headline our task over here, we should better answer those questions first. Okay, here we go. Our first attempt at automatic geometry simplification were only partly successful. For example, on those slides you can see how machine cut almost all details from the character head without affecting the rest of the body dramatically. But such clumsy simplification on the first glance gave us an answer to the question how much to cut, what to cut, and will it help us? With such amount of polygons on the characters, our render starts showing some slight signs of life. Since we couldn't control the after simplifying final character didn't make much sense. The only solution was to work with the construction elements and then reassemble all characters from the beginning. On the slide you can see the roadmap that we took for ourselves while working the characters. That's almost everything here. To reduce the amount of work and not to redo all those thousands of elements that I mentioned before, we wrote a small program that sorted all elements that are used in the game. It also includes details about how often they are used. It's very important. As a result, we simply dropped some of the characters or some body parts that were almost didn't used. We worked with the character's head separately. Since we used bones for face animations, we could reduce head polygons very accurately. And at the end of the day, we were able to reduce the number of polygons and head bones by 2 times. At the same time, the quality of face animations remained at acceptable level. Fortunately, the generation of face animations is fully automated process, which was not very difficult to apply to the new heads. After a few weeks, we were able to achieve acceptable quality by cutting almost 60% of polygons on each characters. At the same time, the other aspects of the game didn't fall apart. So on the slide you can see comparison of the 2 main characters. One is from the Switch and second one is, as far as I remember, PlayStation 4. So couple words about animations. We had to disable closing for entire project. It was taking about 20 milliseconds on Switch, so no way to keep it. And by the way, you should look at turning off per bone motion blur on skeletal mesh components. You can disable it for entire project, but it's still calculated. Is there an easy check box on the skeletal mesh components? It's about 2 milliseconds save. We also played with the animation compressions. We created a table with the testing data to understand what we could pull from each algorithm. After receiving all animations regarding to the algorithm that is better for that animation, we saved a little runtime memory in Switch. So it's almost everything about character optimization. So let's speak about City and what we did there. So the main problem was hitches, especially when streaming, and just general low FPS. Let's start from some meshes, quite simple in terms of geometry, had excessive amount of collision primitives, which led us to long processing of physics scene. Unfortunately, we couldn't find any algorithm to automate this process of reduction such collision primitive. So we went through all static mesh and regenerate the collision or just re-import the model. Sometimes we just turned off collision. It was even better for processing the physics scene. Eventually it was more or less okay. To this day we are not sure what could trigger such collision primitive issue. Maybe it was connected to re-import meshes multiple times through multiple versions of engine. We're not sure. And my recommendation to you, if you see in your profile some issue with collisions with the physics scene, it's where you should look at. Since we were still going through all static meshes, optimizing collision primitives, we were reducing the polygon count of those meshes as well. And here is worth paying a tribute to our 3D team. They were able to cut almost 20 or 30% of polygon and not to lose in visual quality. Basically, we tried to work with static meshes similar as we worked with characters elements. We wrote a rating program for most frequently used meshes, and our 3D artists were optimizing them from the top of the list to the very bottom. After dealing with the physics scene, the hitches while streaming didn't go away completely. Analyzing the situation, we came to the conclusion that the size of the streaming levels, we call it cells, and the streaming radius worked well on PlayStation 4 and Xbox, but not very well on Switch. On the good side, Switch has SSDD, unlike a slow HDD on consoles. Therefore, the situation with EO should much better. After some time spent on experimenting, we could find the cell size in streaming radius that works fine on Switch. In fact, we started loading smaller level more often with less object per cell, which in the end gave us that safety margin so that the player would not face hitches while moving around the city. When we lowered the overall hitch situation in the city, we could move on the specific problematic areas and deal with them manually. It became clear that we would not be able to keep the level of details of the street like it was on consoles. So the art team started removing all extra from the cells from the levels. On average, we had to reduce the detalization from the streets by 25%. In some places we had to cut even more, but of course some places we didn't touch at all. Of course, we sacrificed the quality of the pictures, but in terms of optimizations, it actually killing two birds with one stone. It accelerates the level loading time and increase the general FPS. On the slide you can see the same place but different platforms. So if you're not a 3D artist, I dare you to find the difference. Okay, that's everything about city, so let's speak about render optimization. Working with the static mesh and skeletal mesh brought it results, but let's be honest, it's not that something that will increase your FPS from 5 or 10 to 30. Next, I don't have any fancy slides with the pictures. It will be quite boring slides with a lot of strings. But those very parameters helped us to get target FPS for our project. And disclaimer, I know that not all parameters that I'm going to speak about now are related to render optimization. Don't blame me. I put them here just because I didn't find any better place. And here we go. Changing the quality of anti-aliasing gave us something about 6 milliseconds, but we spent 3 weeks redoing our hair shader. It was a mess. After changing anti-aliasing mode, we had to disable contact shadows. They started to produce noise and artifacts, and plus it gave us 2 millisecond boost from it. We turned off ambient occlusion, generally because of the noise as well, but it brought extra 2 milliseconds for us. I had to disable all shadows except shadows from direction lights. We had to disable lighting shadow bloom feature for direction lights, and to compensate it we had to make light shaft more contrast using parameter light shaft occlusion, parameter mask darkness. Set adaptation type from to basic. Histogram slightly more expensive, and we didn't notice big visual difference between them. By the way, we deleted all reflection captions actors from exterior levels, which gave us more than 150 megabytes of runtime memory and up to 7 milliseconds for render thread. But we still left reflection capture in interiors. We create loads for all geometries that over 1000 triangles. The water shader was reworked as unlit material. And be careful with the skin material. It can give a lot of noise with fast approximate anti-aliasings. For the all particles, we had to turn it off all trails and particle lights. We implement some changes in Atlas Master, such as no global normal, no ambient occlusion, and no adaptive bump. And at that time, volumetric fog was not supported by Switch, and may still not support it, I'm not sure. But without it, we had to reconfigure exponential high fog so it will resemble the one we had earlier. And now a few words about what our programmers did to make sure the game will go live on Switch. The first thing that we did was to migrate from 420 to 422, because there was a lot of things on this version that Epic team did for optimization in general and for the Switch in particular. We also had to maintain a fresh version of SDK for this release as well. And in order to simplify the migration, because it was like migration through two versions, we did not migrate all our tools in editor at that time. We did migrate only those elements that were required directly in the game. The main task for programmers at that time was working on hitches. Our first idea was to play with affinity mask for processes. We tried to share the load more evenly, but after a week of experimenting, it became clear there was no room for maneuver. And in the end, we just revert all back to default values. And to give more room for other threads, we reduced the priority of async loading from normal to lowest. You can see on the slide what we did. At the same time, we create a slightly bigger volume than the perimeter of the each cell level each cell. And if a player ran into that volume before the level was loaded, we would show the loading stream and keep him from falling down. It was like a safe barrier. In order to structure the loading even more, we developed a system of priority level loading. By default, as you know, all maps have the same loading priority. And you can see on the slide our very simple code that we added to world composition CPP. We have chosen the following sequence for ourselves. First we load level logic levels, then exterior, then interior, and then level with landmarks and extra other levels. Profiling has shown us that the calculation of dynamic nav mesh on switch cost a lot, but at that time it wasn't possible to switch to the static nav mesh either. So the following changes that I will speak about now have helped us to optimize the nav mesh calculation for switch. So we checked the checkbox to count the nav mesh only and route the player around the walkers, so we won't calculate nav mesh somewhere in the world. We set up a lazy working thread. This allows us to calculate nav mesh for the new array, not whenever the geometry is added to the world, but when the mesh tile is actually needed to be calculated. We set the nav mesh working thread to lower priority. By default it's normal, but you need to be careful with it. I will speak about it. And by default the game thread is synchronized with nav mesh, so it makes game wait until it calculated. If you set full async nav mesh checkbox in game project file settings to true, the game thread will never wait for nav mesh, which acceptable for the slow-paced game like ours. So as it's for the thread priority, you need to experiment and see if it's okay for your game. And if worth mentioning that starting for 4.24, it's our current engine version for the current project, we give up dynamic nav mesh totally. Since static nav mesh can be cut and streamed with the level, we are using and applying this approach for the current project. It's much more better for us. Garbage collecting, yeah. We had to switch to clustering garbage collecting. It was our main weapon to find with hitches that are related to GC. Switching to this type of garbage collecting was difficult mainly because we developed an entire project without clustering. And when we turned it on, our game crashed all the way. The main crash report looks like this one. The object located in the cluster contained a reference to the object outside the cluster and outside the root space. Steps to fix these issues are quite simple. You find the object, you understand why the cluster is not okay with it. You fix it, you launch the build again, you find another object, you understand why this cluster not okay if not fine with it, you fix it, and so on. In a couple of launches we clean up all the problems that we made. But as turned out, some basic engine classes do not support clustering. For example, widgets. Since we don't have a lot of time and there are basic engine objects, we just flag them as not support clustering objects, and that's all. Before clustering was enabled, we didn't know that the base classes that we use in our editor, like in building editor, character editor, city editor, and extra, were going into the build, even if we are replacing all those objects with Unreal base classes before cooking. It was quite easy to fix. You just need to set editor only flag in your plugin file. It was a small thing, but it's still worth doing because it will save you some memory after all. And I would like to note that although switching to clustering garbage collecting was incredibly difficult and has increased memory consumption to switch after all, it has significantly reduced the hitches associated with GC. So if your game struggles with the garbage collecting hitches, go for it. It's worth it. Oh, that's pretty much everything that I could recall. I hope that this information will be helpful for someone who is optimizing not just for Switch but everywhere. And as for us, this was very useful experience, a possibility to take a challenge and go through it. By a huge thanks to Epic team for their support and help. Without your contribution, porting the game to Switch would be incredibly difficult. My advice to everyone, use the UGN as many as you can. And as I'm not an expert in all aspects of this presentation, for the QA session I asked my colleague to help me with the questions. Thankfully, the format of the talk allowed this. And by the way, you can see on the slide here, on the slide, my contacts. If you have any further questions, feel free to contact me. I will be happy to answer and try to help you as far as I can. So thank you very much. See you. Bye bye.